Hello, it is still Monday, April 20th, and we are ready for science. We finished up our chapter on sound last week, and we are going to continue on to chapter 10, which is talking about light. Now, just like sound using waves, light is going to use the same, it's going to use waves also, but it may look a little bit differently, okay? As you look at the beginning of your chapter on page 237, you see a story here in which someone, an inventor, has to use the knowledge of light in order to make something or invent something that is going to help others. And that's why we study. That's why we study science. Why do I need to know this? So that I can use it to understand it better in order to maybe do something new. This story is really cool because it has to do with World War I, which we are about to enter. We are about to talk about that in our history time. Today we're going to talk about Wilson, and he is the president during World War I. So we're about to get into that history. So this is exciting that this goes right together. And this story is about Marie Curie, who we know for her scientific research in radium, and that she was the first female Nobel Prize winner. But a lot of people don't know her contribution to World War One. And so here is a picture of her in this truck, and this was a mobile X-ray unit. So they had an X-ray machine, but all of the X-ray machines were in the hospitals. And so the soldiers, there were doctors on the front with the soldiers, and they would have a better ability to help them and to be able to do surgery on the soldiers if they had these X-ray machines at the front, but they had to have a way of getting them there. Now remember, an X-ray could be helpful. Why? If I have a bullet wound, remember what happened to Garfield? They couldn't find the bullet. They didn't have the X-ray at that time, so they couldn't figure out where it was. So the X-ray helps them be able to see where the bullet is and then do surgery to take it out, and then hopefully the soldier will survive. So she started looking into, okay, how can we get them up to the front? Now, she wasn't the one who invented the X-ray, but she knew how it worked. So she outfitted these trucks and figured out a way to make them portable and put them in the trucks. And then, well, how are you going to get them there? She can't be the only one that drives all these X-ray machines around. And who was available? Women. The men were serving. They were the soldiers at the front. And so she started training small groups of women to know how to run these X-ray machines and drive the car to the front. And she did the same herself. She taught herself how to drive. She taught herself some basic mechanics in case the car were to break down or have a flat or whatever, and she would have to take care of that too. And then she then drove these machines to the front to help with the soldiers. So I was reading this article. This article is by the Smithsonian Magazine, and it says how Marie Curie brought X-ray machines to the battlefield, and she trained 150 women to operate them. And it says there were no I wonder always how many lives are lost doing this, because it's not just the soldiers that lose their lives. But it says they don't know of any of the women that drove the trucks whose lives were lost, but many of them did have problems later with the overexposure to X-rays. If you know, whenever you've gone to get an X-ray, a lot of times they will give you these heavy aprons to cover the rest of you while you're having an X-ray, because the rays coming from that machine can be harmful. And so a lot of them experienced problems based on this. So here is a picture of an X-ray showing you why you would need one. So you see a bullet here, and then that doctor would be able to go exactly to that point and be able to get that bullet out instead of a bunch of messing around and unnecessary problems. This is another picture of one of her mobile units used by the French Army. she did move from Poland to France, so she was French. And in 1914, when the German army was invading France, she wanted to know how she could help. And she was in the middle of, I read this from this article, she was in the middle of her research with the radium and packed up all her radium, sent it to a safe place in a safety uh, deposit box, basically, until the end of the war so that she could work on these other things and do something that would help the soldiers. So here's some medics at a French hospital, and they are using the x-ray to locate a bullet. And then this is a picture of Marie Curie and her daughter, who also won a Nobel Peace Prize later in her life for her research. And this was taken after the war, though, as they continued to do their research. So I thought that information was really cool. So that was what our beginning story was about, and that is why we study. I'm going to get rid of this for a minute. Oh, I didn't mean to do that. That is why we study. We study so that we can use that information to help others. Okay, now let's look at the beginning part of this chapter where it talks about light energy. So this is page 238. And beside you, as we're going through this, go ahead and tear out your study guide. And this is page 161. And we're just going to be concentrating on the front side of this today. This side is an exercise for the material we're going to read tomorrow, but it's not really the study guide. The study guide are the important pages that really help us understand what's the basic information that we need. So that's what we want to focus on. That's why I skipped a page in your book, because it's a lot of repetition, and we want to just focus on the study guide pages. Okay, so let's look at this. We're going to start looking at this together. Light energy. The people who first discovered X-rays many years before World War I were surprised and amazed by what these mysterious rays could do. It was as if they were a kind of invisible light that could shine right through solid objects. X-rays share many of the same characteristics with light that you can see. Okay, so here is what light is. Light is a form of wave energy. Light is a form of wave energy. It is constantly moving throughout the universe. A light ray travels in a straight line, but the matter around it moves up and down. Light waves spread out as they move away from the source, like ripples of water move away from the place a pebble is dropped. So here, and then it goes out in ripples. However, light travels much faster than water. If you could travel at the speed of light, you would be able to go around the world about 7.5 times in just 1 second. Okay, so look at number 1 on your study guide. What is a form of wave energy that travels in a straight line? What did we just say? What is a form of wave energy that travels in a straight line? Light. Light. Though light waves carry energy just as other waves do, light waves are different from many other kinds of waves. The energy of water waves and sound waves must move through matter. Light waves, though, can move through both matter and empty space. Okay, so that's interesting. Because light waves can travel through space, light from the sun and other stars can reach the earth. Do you think that was a design? Do you think God designed it on purpose to travel through empty space so that we could have the light from those objects? Absolutely. So look at number 2. Light waves can move through both blank and empty space. So what's the other one? Both matter and empty space. Okay. Light waves also move faster than other types of waves, such as sound. Oh, there's a really cool video. If you want to look this up, this is Mythbusters, and they do this experiment with the speed of sound and light. So they have someone looking, and they have someone whose eyes are closed, but they're listening. And then they have an explosion in the distance, and they have the person raise their hand when they either see, if they're the seeing person, or they hear, if they're the hearing person. And who raises their hand first? Well, if light travels faster, the person who's seeing it sees it before the person who hears it. And that's really cool. If you want to look up that video, look that up. And I would just put in Mythbusters speed of light and sound, and maybe that'll help you. Light can travel through space at about 300,000 kilometers per second. The sun is about 150 million kilometers away from the Earth. Yet light from the sun reaches the Earth in about 8 minutes. Scientists do not know of anything that can travel faster than light does. Okay, so read about Galileo down at the bottom. It is going to tell you some about science and history. Don't miss that. But I'm going to keep reading on to the next page. Comparing waves. Sometimes scientists classify waves by whether or not they can move through empty space. Waves that can move through space are called electromagnetic waves. Light is an electromagnetic wave. Number 3. Waves that can move only through matter, such as sound waves, are called mechanical waves. And we talked about that last chapter, didn't we? You identified sound as a mechanical wave. Now you have something to compare it to, okay? Sound is mechanical because it moves through matter. Light is electromagnetic because it doesn't need matter. Scientists also classify waves by the direction in which they move. Sound waves move in the same direction as the matter is vibrating. Waves that travel this way are called longitudinal waves. Light waves move differently. If you make a wave with a rope, you can see the wave traveling from one end of the rope to the other. As the wave travels forward, the rope moves up and down. So the wave is moving along that rope and it's traveling this way. The direction that the wave travels is perpendicular to the up and down movement of the rope. This is an example of a transverse wave. Waves that move perpendicular to the way that the matter is moving are called transverse waves. Light waves are an example of transverse waves. So you see a really good example in your book there. This is a girl who's taking that rope and she's moving it up and down, and that is a transverse wave. It is going up and down, and then the wave is moving this way. So the arrows are perpendicular. This is longitudinal, and this is what we talked about with sound. It's all moving this direction, okay? You don't have it going up and down like the string. So, look at number 8. Is this true or false? Waves that move perpendicular to the way that matter is moving are called transverse waves. Is that what it says on page 239? Waves that move perpendicular to the way that the matter is moving are called transverse waves. So that would be true. Look at 7. Light waves travel slower than sound waves do. Is that true or false? False. Light waves travel faster. So in the blank you would put faster. The first thing God created was sound. Is that true? No, the first thing God created was light. Light. And, okay, let's keep going. So, look at the next page, page 240. Properties of waves. So, here's where we're going to identify some of those different parts of the wave that we're seeing. There are many different kinds of waves. Some are tall, others are short, some move quickly, but others move slowly. All waves, though, have the same basic properties or characteristics. These properties include wavelength, amplitude, frequency, and speed. So that just said all waves have the same basic properties. Look at number 9. All waves have the same basic properties. True or false? True. Okay. Now, transverse waves look like a series of hills and valleys. So like this. Woo-hoo. The top part of the hill is called the crest. So label it there on your study guide picture here. Okay, so we are labeling 10 through 13. The top part of the hill, right here, is the crest. This is the highest point of a wave. The trough is the lowest point or valley of a wave. So in your diagram here, that would be this number. Okay, number 13 is the trough. It's the low point. Crest, trough. Scientists use the crest and troughs of a transverse wave to measure the length of that wave. Its wavelength is the distance between two crests or between two troughs. Waves with short wavelengths have more energy than waves with long wavelengths. So, look, trough to trough, this is wavelength. So this number is going to be labeled as wavelength. This could also be up here. Crest to crest or trough to trough is how they measure wavelengths. Another property of a wave is its amplitude. Amplitude is the height of a wave. If you stretch a rope tightly, it will be in a straight line. Think of this straight line as a rest position of a wave. Moving one end of the rope will make the rope vibrate up and down. Part of the rope will move above the rest position and make the crest, and the rope will also move below, forming the troughs. The distance that the rope moves above or below the rest is the amplitude or height. So here where it's got this is your rest position. Between the rest and the crest, ooh, that rhymes. Between the rest and the crest is called the amplitude. It's the height of the wave. You could also do it here, okay? From the rest to the trough or the rest to the crest is called the amplitude. So look at number 4. What is the height of a wave? What's the word? Amplitude. Amplitude. The what of a transverse wave is the distance between two crests or between two troughs. We said that before. So what was this one? Wavelength. So that's what you're going to put for number 5. The wavelength is the distance between two crests or two troughs. Okay, now I'm on page 241. As the rope moves up and down, many waves move through it. Each wave has a crest and a trough. You can count the waves passing a point by counting either their crest or their troughs. The number of waves that pass a certain point in 1 second is the frequency of that wave. A wave's frequency is not the same as its speed. Frequency refers to how many waves pass by a point in 1 second. Speed refers to the distance that one wave travels in 1 second. All waves have specific speeds, frequencies, amplitudes, and wavelengths. So, speed and frequency should sound familiar to you because we talked about that with sound because it's a wave also. So you still have those same properties. So here, the top one says the frequency is 7 and the frequency is 9. Okay, so how many that you can count. So, number 14, what is the difference between frequency and speed? And you can see those definitions right there on page 241. So, frequency is the number that pass a point, and speed is the distance that it travels. And then define electromagnetic and mechanical waves. Which one is sound and why? So if we go back to page 239, it talks about electromagnetic and mechanical. Electromagnetic does not need matter. Mechanical needs matter. Sound is mechanical because it needs matter. That's it. Okay, so make sure you get those answers down there, and we'll go to the next section tomorrow. in the comments below, I want you to think of another invention. We talked about Marie Curie and her and X-rays that had to use the knowledge of light in order to be able to tell us information. Think of another information that uses the understanding of light. I'm sorry, I think I said the wrong word. Another invention. Think of another invention that uses the understanding of light to make it work. Okay? You can even look it up if you need some help looking some things up, but think of an invention that would use the understanding of light. Go.